about blockchain secured acoustic signature authentication for military command communication in SWAM intelligence operations. Yep, these are my group mates, and supervisor is Mr. Kaliwango Marvin. Okay, so background of our problem. So the background of our problem, military operations nowadays making use of SWAM intelligence techniques for for executing their missions. For example, the use of UAVs. These are like drones and maybe robots in some cases. All these need to coordinate and achieve the goals they're supposed to achieve properly. So existing systems are using the command and control infrastructures. This is where a group of technical experts sits at a base, let's say at at an official building, and then they command these SWAM intelligent devices like the drones. They command them manually, like through a computer, to go and let's say do what they're supposed to do, let's say bomb an area and then come back. Yep. And the challenges with this is commands can be spoofed, channels can be hacked, and someone else can hack the system and make the drones do all that kind of thing. So our work, we are trying to integrate acoustic signature authentication to make sure that commands aren't spoofed, and then also audio steganography. This hides commands and noise, such that even if someone manages to tap the communication channel, they won't be able to understand anything. And then a blockchain ledger, that's for validating and storing commands in a decentralized way without a central database. And then a SWAM consensus. Yeah, this is to ensure that when, let's say, one element of the SWAM is away or dies out, the SWAM can still continue to function. Yeah, and so not waste time on that. Okay. So for the related works, blockchain has been used in military systems. It has been used for secure communication and data integrity, preventing tampering and unauthorized access, enabling trustful and decentralized coordination. And then for acoustic voice authentication, this is more of using voice prints and extracting features from those voice prints to distinguish users, and maybe also detecting deepfakes and spoofing. That's the same thing. Then SWAM intelligence and coordination. This is a concept that inspired by SWAM insects. Things like bees, ants, rodents, termites, insects that live and work together. Yeah. So it enables these systems to be self-organized and fault tolerant. When one element of the SWAM dies out, that doesn't affect the overall performance of the SWAM. Yeah. And then common algorithms, the ones that currently exist, is the particle SWAM optimization and colony optimization. These are more of pathfinding algorithms. Yeah, so for our contribution, we are combining blockchain and acoustic authentication and SWAM consensus. And it's supposed to, this is supposed to work in areas where, the connection is low. Because as I mentioned earlier, with command and control, there is a set of technical experts in a certain centralized office, and they're trying to issue commands to these SWAM elements, which are already in the field. So in case there is a poor connection here, all these operations are hindered. So as we want to make sure that these can go on even when there is these operations can go on without the central command center. Yeah. And also this, while also ensuring that it's tamper-proof and voice verified.
Well, we'll split the problem statement into two parts, one being the domain application problem. Here we have a decentralized C2 systems, and we know they're easy to hack or jam, and there is a risk of scoped commands and fake identities. Someone can fake to be the commander, and then they give a command, and this can lead to mission failures, and it can lead to death of people. And the other problem with loss of communication can lead to mission failure. Talks about that, and the need for secure, fast, offline verified control commander's voice using acoustic features like MFCCs, and hide commands using audio stenography, like in noises, so that in case of an interception, no, the intruder cannot know what exactly the message is, unless they do have like part of the key. Reach some consensus via blockchain validations, then detect spoofing, deepfakes operating on offline, radio denied zones. And to guide our research, we asked a few questions. And one of the questions is like, can a commander's voice be used as a reliable authentication signal in the field? And yes, because it has unique features, as you're going to see in the implementation or the architecture of this system. And also, how can we secure communication in the unmanned systems, the drones, in a swarm without a centralized control? And how can blockchain and acoustic stenography enhance trust and prevent spoofing in the military C2 systems? We are going to see all that in our architecture. And also, we had some objectives, and the main objective is to design a multi-layered security framework that uses acoustic biometric authentication, audio stenography, and blockchain for consensus to ensure C2 communications from intelligence systems, and also to implement an acoustic signature authentication using voice print features like the MFCCs, the page to verify the identity of authorized commanders in real time, among others. Well, our contributions or the outputs in this research, we have developed a secure acoustic blockchain framework for storm communication. We built an offline fast model to use in jammed or GPS denied zones, like in war zones or areas with disasters. And also, like, we've implemented voice print authentication using sound physics and acoustic features that are unique to every voice. And also, we built like an acoustic consensus system for storm verification.
My name is Hendrik Shami, and I will continue on with the methodology and the preliminary results sections. The protocol starts from the commander's device, and from the commander's device, we want to generate the uniqueness of this particular message that's going to be passed, and we want to also record the uniqueness of this commander's device plus the uniqueness of the commander himself or herself. And in order to get the uniqueness of this commander, we are going to record the impulse response. And we are going to generate, in order to do that, we are going to generate a signal coming from the commander's device. And we are going to record the echoes coming from the mouth, the face, and the vocal tract of the commander's device as they are recording their message. We are going to extract acoustic features, then hash the message plus the DCR probe, and then we are going to sign it with the generated ephemeral keys for this particular message, this communication happening at that time. After that, we are going to send the packet, the entire packet. We're going to split it into two parts for transmission, and we're going to send the first part A plus the signature to the audible signal that can be heard by anyone. And we are going to send the key part B plus the DCRR to the inaudible signal, to the ultrasonic frequency range. And once each agent have received the packet, they are going to reassemble the packet. And the first thing they're going to do is to check if the parts, the cryptographic keys they have gotten, the two parts, do they make sense? Does the public and the private key rules, are they followed in this particular instance? If so, we are going to move on to the second check. The second check is the liveliness check. We are going to see if this commander is real, and you are going to check for the particular resonance in the voices the vocal signal that we got from the commander. Is there enough resonance and variety in order to say that this is a particular real human being speaking? If that second check is passed, we are moving on to the attenuation verification. Here we are going to check if the commander is at certain varying distances between the agents. because the agents are going to be displaced at certain distances, not at the same distance. So we expect that the received signal is going to be different for each agent. So once an agent has been able to generate or has been able to go through these checks, we are going to broadcast the confirmation, whatever confirmation the agent has come up with, and then we are going to obey to the quorum. The quorum, we are going to set it to a certain flexible number. Could be 80%, could be 70%. If it's 80%, we are looking if all the agents have agreed at 80% that the 80% available agents have agreed and have confirmed that this is the real commander and this is the command that the commander wants to be executed. If so, then we can commit the command on the blockchain and then execute the command. And then from there, we can also do some optimization as these agents are executing the command. We also want to optimize the optimization so that the performance for the next execution can be improved. This protocol is actually split into 3 phases. So I've just explained the overall architecture. So all these phases are included in them. And in order to try out if this protocol could work in the real world, we've tried some experiments and simulation where we've used real human voices and also at the same time synthetic audio generation for generating synthetic audios or artificial audios. And we did mostly audio filtering and hyper transform in order to get the particular frequency channels we're looking for. For example, we wanted the ultrasonic 20 kilohertz frequency, so we wanted to use a high pass filter, actually a low pass filter, in order to get the particular audible command, and then also use a high pass filter to get the hidden message. And then we apply some modulation in order to hide our embedded message into the high frequency range. And then we did a simulation with the following results. We were able to verify that we can be able to split the different channels. The 20 kilohertz channel can be split from the 0 to 5,000 channel. This is the audible channel. And the inaudible channel can be split successfully. And here we can show the sine wave that we generated synthetically or artificially. And we were able to split the command and then modulate it and send it to the 20 kilohertz. Actually, we can see the spectrum here. This is the original audio that was ranging from 0 to 5,000 hertz. This is audible, an audible signal someone can hear. And we were able to modulate the signal to 20 kilohertz and then embed our message there. And also we were trying to simulate, this is actually coming from the simulation, where we try to see if the noise is increasing. Can we be able to tell if the commander is real or not? So for this case, we are expecting noise from the commander so that we know this is a real human being. So if the noise is actually left to the bare minimum in the range of -30 up to 70, so we know this is too good to be a real human being speaking. So we were expecting some noises and variations. So we know that below this certain received signal strength indicator values, we can tell that this person is not real. So they are trying to spoof the system. Yes, so this is what so far we've come up with.
Conclusions. So we're able to design the conclusion and limitation, able to design a new control protocol called the D-AVAP, the Dynamic Attenuation Verified Acoustic Protocol. Then we integrated the metric feature extraction and ephemeral key generation. We also incorporated a multi-channel steganographic packet assembly. Then we designed multi-layered verification and attenuation-based processors. We built system optimization parameter heuristics from intelligence. So limitations, the need for ultrasonic capable device prototypes, and then the environment situation. Since it's very difficult to create the exact simulation, or that's the exact environment simulation, as that in a water vision, which is very unpredictable. So the next steps, we have to combine blockchain, caustic authentication and Swarm processes, to develop an offline, perfect, secure command sharing protocol, then build a tamper-proof, voice-verified military network, and simulate a Swarm optimization environment. So take this opportunity to thank the university for providing us with the community and resources for this project. I'd also now take my sincere gratitude to Mr. Lolinganga, our supervisor, who has been a great support to us through his continuous feedback and support. Then acknowledgement goes to Dr. Rosna Chibule, whose insightful suggestions and constructive challenges greatly contributed to the shaping of this project idea. Then my fellow colleagues, who we worked tirelessly, spent some nights off to come up with this project. Thank you so much.